Hi everyone, my name is Shreyas Vissapragada, and I'm a fifth-year PhD student at Caltech. And today I'll be talking a little bit about our project studying the atmospheric evolution of 3 young planets in the V1298 Tau system. This is work that I've done with my advisor Heather Knudsen, along with all of the collaborators you see on the screen. First, I'm going to be talking about the evolving atmospheres of young planets and why this topic might be astrobiologically relevant. Then I'm going to talk about how we actually make observations of atmospheric evolution in young planets, and in particular, I'll be discussing a technique called helium photometry. And finally, I'll discuss our recent results applying helium photometry to the planets in the V1298 Tau system, and I'll motivate some future work that I hope will get done over the next few years. The fundamental question that we're trying to answer is how do planetary atmospheres change over time? To situate ourselves, the majority of extrasolar planets, planets orbiting stars that are not our Sun, orbit quite close to their host stars, within an orbital period of 100 days or so. This means that these planets are getting constantly bombarded by high-energy radiation, and that can really change how the planet looks to us and how the planet evolves over its lifetime. Consider a hydrogen atom living in an exoplanet atmosphere. Because the planet is so irradiated, that hydrogen atom is going to see an extreme ultraviolet photon with energy exceeding 13.6 electron volts quite often. And what that photon can do is it can ionize the hydrogen atom. But if the photon energy exceeds 13.6 eV, that excess energy has to go somewhere, and it goes into heating the gas. It goes into the thermal energy of the planetary atmosphere. And as this happens many times, because the planet is severely irradiated, for many hydrogen and helium atoms in the planetary atmosphere, the net effect is the planetary atmosphere can heat up so much that it becomes gravitationally unbound, that the planetary atmosphere is just lost. And we can imagine that this has pretty important consequences for the planetary mass, as the material is literally being lost from the system, for the planetary radius as well, as I'll show in a second, and also for habitability. The presence or absence of an atmosphere is known to be quite astrobiologically relevant, and so understanding the primary factors that control whether a planet can retain or whether it loses an atmosphere is of utmost importance in astrobiology. Now, to briefly mention one consequence of atmospheric evolution, we can take a look at the histogram of observed exoplanet radii from B.J. Fulton's work done in 2018. What's being shown here is the average number of planets per star as a function of planetary size, and I've indicated the sizes of Earth, Neptune, and Jupiter for reference. And while you can see that the most common type of planet that's been discovered to date is something between the size of the Earth and Neptune, we can see that the distribution is pretty bimodal. And actually this has a lot to do with atmospheric evolution. We think that planets on the large side of this radius gap, called sub-Neptunes, at around 2.5 Earth radii, we think that these planets retained most of their atmosphere against the effects of atmospheric escape. And we think planets on the small side of the radius gap, at around 1.5 Earth radii, we think that they lost their atmospheres. And so clearly atmospheric evolution has an outsized impact on how planets appear to us, and how planets evolve over their lifetimes. Now, to understand when this process is happening over a planet's lifetime, it's necessary to look at the high-energy radiation of the host star. And what's being plotted here is the X-ray luminosity of 3 different stellar models with different rotation rates as a function of stellar age. And you can see that for all 3 models, the star is outputting much more X-ray luminosity over the first 100 million years or so of its life. And what that leads us to conclude is that we should try to observe atmospheric escape when it's happening to planets that are less than around 100 million years old or so. Now the problem is that most planets that have ever been discovered are about a gigayear or older. Most of these planets are positively ancient, compared to the timescales on which atmospheric escape happens. So the problem is we've never observed how the atmospheres of young planets evolved before. And this really prevents us from answering the question, how efficiently can young planets turn radiation into heat? This is the primary control on whether a planet keeps or loses its atmosphere, and so this quantity is of utmost astrobiological relevance. To remedy this, we looked at the young transiting system V1298 Tau, which was discovered by Trevor David in 2019. Now, I'll clarify what transiting means in a second, but basically it just means that the planets pass in front of the host star with respect to our line of sight. Now, this system is 23 million years old, so it's young enough for us to observe atmospheric escape occurring in action. There are 3 known planets in the system: planet C, with orbital period 8 days and a size about half that of Jupiter; planet D, with orbital period 12 days and a little bit larger than planet C; and then planet B, with orbital period 24 days and a size about that of Jupiter. So now that we've selected a target, we can ask, how do we observe atmospheric escape in action? One way to do this is with a technique called transit spectroscopy. So in the transit method, we're watching planets as they pass in front of their host stars and block out a little bit of the star's light. And larger planets block out proportionally more light from the host star. Now we can visualize this diagram in this very not-to-scale cartoon shown here. And again, some light from the host star will be blocked by the planet and won't reach your telescope. During a transit, I should say, but some of the light will reach your telescope, and this is kind of the nominal case. However, when a planet's atmosphere is escaping, some of that light is actually getting filtered through that low-density escaping atmosphere. And if we can choose to observe at a wavelength where that low-density tenuous gas becomes opaque, then suddenly the planet will absorb, it'll block out much more light, and the planet will appear much larger to us. So now I'll quickly describe how we make these measurements in practice with helium photometry. So our experimental design is pretty simple. We take light from the telescope, we pass it through an optical element called an engineered diffuser, which just helps us control systematics. That light then goes through an ultra-narrow bandpass filter that is centered on that 1083 nanometer line. And then it forms our image, where we can take a picture, much like you would take a picture with your iPhone camera, except that we take it in the infrared. And we take many, many, many pictures over the course of a night, and we track the star's brightness in all of those pictures to form a light curve. And based on how much light gets blocked out during the planetary transit, we can tell whether or not helium absorption is going on in the planetary atmosphere, and in so doing, we can tell how quickly that planet is losing mass. So here's an example of a measurement we made when we were commissioning this observing mode of the planet WASP-69b. Now this planet, when observed at other less special wavelengths, looks like this in the blue. What's being shown here is the star's brightness over time, and you can see that the planet at the transit center is blocking out a little less than 2% of the star's light. However, when we measured it at 1083 nanometers, we got the data in gray, which are binned in black and shown with our best fit model in red. And clearly at 1083 nanometers, the planet blocks out more than 2% of the star's light. And so we use this measurement to confirm the presence of helium in the atmosphere of WASP-69b at 10.1 sigma confidence. Now, this system is pretty old, so it doesn't tell us about what's going on when atmospheric escape is most important for a planet's life, but it helped us understand how our instrument worked, and it helped us confirm that everything was working as we expected. So in this work, we applied this technique to the planets in the V1298 Tau system, and now we'll describe some of the results that we saw. When we looked at the transit of V1298 Tau C, we weren't able to detect anything at all. Our light curve is shown on the left, with data in gray, binned in black, with a best fit model in the solid line and the model for the transit at non-1083 nanometer wavelengths in the dashed line. And I've also shown a baseline model for just showing how the star and the weather evolve over the night in red. And you can see that the model, the solid line, doesn't really indicate that we detected a transit at any confidence. This is kind of disappointing, and it's probably due to poor weather, which, sometimes you get unlucky. But at the same time, we can definitely rule out a very large transit in the helium line, which is an important result in and of itself. When we looked at planet B, I've shown the same thing for planet B on the right, we did detect the transit of this planet, but we don't think we detected any clear helium absorption. Our best fit model is shown on the right in the solid green line, and the dashed green line shows the best fit model at non-1083 nanometer wavelengths. And you can see that the models kind of overlie each other. They have slightly different shapes, but they're not really distinguishable in any statistically significant way. So a larger transit in the helium line is still possible, but we would definitely need more data to confirm that. Now, when we looked at planet D, we think we see a tentative detection. Now, we took 2 nights of data on this planet, which are shown with the circles and triangles in the light curve on the left, and the signal appears consistent in amplitude across both nights of data collection, which is really exciting. However, to stitch this light curve together, we did require a transit timing offset, which is a slight deviation from a Keplerian orbit, and that was enough to make us a bit hesitant about the result, and so we're calling it a tentative detection rather than a slam dunk. Still, it's a really interesting result, and it means that this planet should be prioritized for future follow-up. To summarize our work, we are attempting to measure atmospheric escape from young planets for the first time. And here's a graphic of the geometry of what we're actually measuring. Now, we tentatively detect helium absorption for V1298 Tau d, which indicates that this might be the first known young planet with observationally accessible mass loss. And in the future, we'd of course like to get more data, which we'll be hopefully gathering some more full transits in the winter, weather permitting. And we'd also like to measure the planetary masses to know the gravitational potentials from which these planets' atmospheres may be escaping. That's all I've got. Thank you so much for your attention.